Go ahead. So today I'm going to talk about the paper published in Science Advances, and it named episodic growth of Physic continents in the past 3.7 billion years ago. And the first author, it has only one author, and Marian Gargan, and now he's working at the Grandmont Avenue University, and he got his bachelor degree of the physics and chemistry at the University of Grenoble, and got his master and PhD degree at the Earth Science, also at the University of Grenoble. And this speech contains 4 parts. The first is background knowledge, and then is content composition. That is first scientific question of this paper. And then is the content growth. That is second scientific question. Last but not least, as conclusion. Our Earth's surface consists of the less dense and more philosophic continental crust and more dense and mafic oceanic crust. Actually, the evolution of the continental crust and formation is an important geological event in the early Earth. And it's highly related to the transition of tectonic settings, and also affects the global geochemical cycles and related to the evolution of early life. Actually, there are 2 important scientific questions about the continental formation. The first is whether the continental crust has grown by plus continuously. And actually, some scientists has realized that the geological records of continents formation, such as zircon, show some episodic pattern through time. For example, the zircon's age distribution shows some periods, that is peak and valley, and it may reflect the episodic growth of continents through time. But other scientists propose that these geological records may be explained by preservation or sampling bias. So it's under debate. Another question is the composition of continental crust has changed through time. In previous studies, some scientists proposed that using the trace element ratios of igneous rocks or the sedimentary rocks to reconstruct the chemical composition of continental crust through time. And they proposed that the composition changed from mafic to more philosic during 3 to 2.5 billion years ago. But recently, more and more evidence have shown that the composition of continental crust might be more philosic in the early years. For example, the PATAC 2020 used the 3 members calculation combined with the sedimentary and igneous datasets, and they found that the continental composition may be more philosic since about 3.5 billion years ago. Alex Leaf used the sedimentary rocks, also gets the same conclusions. And also Curler and Harrison used the constant silicon model of igneous rocks and also proposed the same conclusions. But this problem is also under debate. So for this paper, the first scientific question is continental composition. So in this paper, they also use the Sumerian and Neodymian isotope composition to reconstruct the chemical composition of continental crust through time. Let's see its rationale. So for Sumerian and Neodymian elements, both of them are weakly mobile during the chemical weathering and diagenesis of sedimentary process. And also, their ratio is not largely fractionated during minor salting. Thus, it may mirror its source characteristics. And then, Sumerian neodymium isotopic compositions of sedimentary rocks, including the fine and coarse detritus, to reconstruct the composition of continental crust through time. So let's see the process. So this figure shows the raw data distribution. They got about 2,500 samples here. That is Sumerian neodymium isotopic compositions with time. And they also compiled the silicate oxide content and the isotopic ratios of the igneous rock. And they find some good correlation between the two variables. And then they just use these sedimentary rocks isotopic ratios and this relation to reconstruct the silicate oxide contents through time. You can see that the bin is 200 million years. It's pretty large, because it did not have too many samples here. And they got the conclusion that the upper continental crust may be more Phaeocic since the 3.7 billion years ago. But I have to give a comment of this part. This figure from the supplementary fires, you can see the Archean and post-Archean pattern or relation is different. Use these two different to reconstruct the chemical composition of continental crust. They will get some different pattern. But they also just propose that this difference will not influence their conclusions. But we have to be careful about it. In previous studies, also usually use the trace element and their ratios to reconstruct the chemical compositions change. And in the 2020, Curly Harrison proposed that the trace element ratios with the relation of these two, the trace element ratios and silicate oxide pattern of relation are variables in different ages. For example, for this rubidium to strontium ratio, you can see that they have different relation in the Phaeocic end member. So using the trace element or its ratios to infer the major element content through time is suspicious. Probably this problem also exists in using the Sumerian neodymium isotope compositions to reconstruct the pattern. But anyway, let's back to the figure. So in this figure, they also just reconstruct the silicate oxide content change through time. And we can see that the chemical composition of continental crust may be more Phaeocic and in the early years, and appears the andesitic composition. So how to explain the andesitic composition of the continental crust? Actually, there are two explanations. The first is that this andesitic composition may reflect the main silicate oxide contents of biodermal distribution of continental crust. It means that this intermediate composition reflects the mixing of these two end members. If it is right, and they also could use these two end members to calculate the relative proportion of these two end members through time. And there exists another explanation. In 2014, Xinti Li just proposed that this andesitic composition of continental crust may represent the average composition of evolved silicate melts produced by the crystal melt segregation of basaltic magmas in deep crust. It means that the crystallization of some special minerals could also responsible for this intermediate composition of continental crust. But it's still under debate. They also did not get any conclusions from these two explanations. And then it's about the continental growth. In this paper, they just used the neodymium model age to reconstruct the continental growth pattern. Neodymium model age is the average age at which the continents will extract from the depleted mantle. Actually, this neodymium model age of continental crust usually has three contributors, including the geomenal, reworked, and recycled crust. But in this paper, they also assume that the reworked and the recycled crust have the same neodymium isotope compositions. So in this paper, they just use the neodymium model age of sedimentary rocks to reconstruct the geometric crust growth. Let's see that this orange shadow just shows the geometric crust, continental crust growth periods, and it indicating by the shift of the neodymium model ages of sedimentary rocks, and it's away from the reworked crust. Also, this paper also calculates the relative proportion of geometric crust from neodymium model age of sedimentary rocks. Here, I'm not going to talk about more equations of this part. If you're interested, you could see the supplementary files of this paper. And also, there are another problem. So, is it possible to determine the absolute volume of continental crust over time? Here, they also only calculate the relative proportion of the geometric crust through time. But how could we determine the volume of continental crust through time? Quantifying the absolute volume of continental crust through time requires to know how the crust recycling through time. But it's really difficult to get appropriate parameters through time. Here, they also just simplify it. It uses the parameter beta. Beta means the proportion x of recycled and geometric crust at any time. For example, in past 200 and 600 million years, the beta is 1. Here, it means that the recycling of the rate of recycling of crust is equal to the production of new crust. That means the no net growth of crust through time. So you can see total growth has no change. Here, if the beta is 0, it means that there's no recycling of crust. The total crust will all become the geometric crust. But it also point out that it's very difficult to get appropriate beta values through time. But whatever the past recycling rates, this figure just shows that the volume of geometric crust is not constant but episodic, because the episodic through time. It means that the continental growth may be episodic through time. And it also has some problem, is that the episodic growth of continents reflect episodic production of felsic crust, or it just to reflect the artifacts, as we discussed above, just to reflect the preservation or sampling bias. So the paper this also tried to talk about these two problems. The first is the selective preservation or sampling or preservation bias. Actually, it's reflected by the irregularity of the rock record available for sampling. And if the preservation bias is responsible for the episodic growth of continents through time, you could see the relation between the relative proportion of germinal crust and the number of available Sumerian neodymium data. And unfortunately, I see the supplementary files of this paper, but they did not provide the supplementary S8. I think maybe it's an error of their work. But forget it if this figure exists and there is no correlation between these two variables. And we could say that the selective preservation or preservation bias could not be responsible for the episodic growth of continents. Another problem is sampling bias. And it's different from the preservation bias because preservation bias actually it is the preservation potential of the sedimentary rock record. But the sampling bias just talk about the preferential erosion of germinal crust in the source area. More specifically, it could be named erosion effect. So let's look more details of this effect. So the preferential exposure of high reliefs or the high latitude of germinal crust, where the erosion is maximum, and it will lead to the presumable overrepresentation of the germinal crust in sediments. And in other words, it means that the higher of the germinal crust is, and it's more easier to be erosion, and it will translate into the sedimentary record. So they also just compiled the modern river sediment load and about the elevation. We could see that these two variables have good correlation. So the erosion is maximum in areas of higher topography. There exists this relation. And also just compiled the epsilon neodymium values of these sediments load. And this direction is the germinal crust direction. And we could not see the correlation between these two variables. So there's no correlation between them. So there's no obvious topography relation related to sampling bias in the neodymium stratigraphic record of sedimentary rocks in global scale. And this is the first time to test this problem in global scale. And so it is very interesting. So they also just conclude here that the Earth's continental growth grows as the episodic through time, and it could not expand by the preservation or sampling bias. So what about the mechanism that control the continental growth as the episodic pattern? They also just compiled some other geological records that is the Durkan's age. And when we just put the continental growth pattern and the Durkan record, these peaks broadly correspond to these previous Durkan records, but not accurately. Partly because these Durkans may reflect some regional scale pattern, and also because we know the age area of this study is pretty large, about 200 million years. So this large area may affect the results or the correlation between other geological records. And also, they also just compiled some large igneous province events data. just there's also no obvious correlation between these two variables. But interesting, they also just point out that the recurrence of the episodic pattern of continental growth is 500 to 700 million years. And supercontinental cycles is also the 500 million years. Maybe it's related, but actually they could not correlate well if you just put them together. So it's also on the debate. Maybe it could be solved in future studies, but it cannot be solved in this study. There's some conclusions. So in this study, they also choose this Sumerian neodymium isotopy ratios to reconstruct the composition of continental grass through time, and also use the neodymium model age of sedimentary rocks and constrain the episodic growth of continents through time. Actually, this paper put some interesting methods and it solves some problems, but also leaves some scientific questions to be unsolved, maybe need some future studies to solve it. So that's the end. Thank you.
Okay, thank you, Chengkao, for leading this session. Actually, I have a quick question that regarding the. Do you think that so what's the time resolution in this study? As they point out, the 500 to 700 million year cycle.
Yes,
is that like in 100 million years they have one being? And then
because we only have they also just get out 2,500 data on the whole. I think 4 billion years. I think the data is too much small, and so the being is pretty large. It's about 200 million years. So the arrow, age arrow is pretty large. Hello, could you hear me?
A little bit, right?
Sorry, I didn't hear.
Okay. I think their time resolution is pretty poor, and then we call episodic.
Yeah. I think the
conclusion looks very fuzzy. Every being, then you have a being that's a little bit low.
It's pretty low. I think at least 200 million years error for this episodic, because we can see that it's 500 to 700 million recurrence. It means that it at least 200 million years error.
So actually, I don't know that for sedimentary samples, are the neodymium isotopes very rare and to do it like say in recent 1 or 2 decades, or it's a really old one people have done again and again for several decades?
Actually, I think they also just exclude some data. They just include the fire and coarse detectors, and I think it did not have some mailing source to compile so much data. And a lot of data could not be used because some data may be outliers and affected by the sedimentary process.
Because to me, if you have a sample number, then they have more neodymium bulk rock samples. At least I would guess I said more than 2,500 for igneous rocks.
Also, they did not compile 2 million igneous rocks. They just compiled about 300 300 samples here. That's why I guess that if you use different ages igneous to plot these two variables in different times, it will give different relations.
Okay.
That's the problem, I think. So why I just give comment here.
Yeah, I think they might also do some, I don't know.
Yeah.
Because if they want to be self-consistent, I don't know how they are going to compare with Patek or what Tommy in 2016 paper in terms of the ratios to show the different element member mixing. Because I don't know whether those using the same data sets are self-consistent between the elemental ratios as well as the neodymium isotopes.
Yes, I think they did not give any comments of previous studies, and actually, I think they used the same idea just as Tommy in 2016, because in Tommy's paper just used the sedimentary, tri-sedimentary of igneous, and also the ratios of igneous rocks. I think they just use the same ideas to do this work. And this paper just based on their previous published paper in 2017 and GCA, they just find some really good correlation of igneous rocks, just as shown in this figure B. That's the silicate oxide content just covered wheel with the samarium neodymium ratios, isotope ratios. They just maybe these samarium neodymium ratios could reflect the silicate oxide contents.
Okay. Okay. Other questions from other participants?
Yeah. Hi, Chuntao.
Yeah.
So, I have a question about the figure 4. So they are trying to prove that the ND isotope is no relationship with erosion, right?
You mean this figure? The figure, this one, or that one?
Okay. Yeah. Figure 4B.
Yeah.
Okay.
So
yeah.
If the correlation between the sedimentary load and the epsilon neodymium value, if they correlate well, it means that the juvenile crust or the higher attitude of the juvenile crust will be more easier to be recorded in sedimentary records, and it is the erosion effect. But here, there's no correlation, so maybe the erosion effect may be not so important in this study.
Okay. So in the figure 4A, and they are seeing that, but I don't think the figure A is right, because you know if you have the more elevation, and you can have you can have a longer river, so you can have more load, right? Not the
Yes, maybe the longer the river is, the more sediments it will get.
Yes, but they are saying that because they think because the more erosion, because the more the thing, if you have more elevation, then you have more erosion, so you can have the more load sediments load. Now,
Yeah,
is that
yes.
same?
Yes. Maybe they should consider the sediment source of these rivers. If the river is too long, it will get some other sediments from other sources, not from these high relation areas. Yes, maybe you could ask these questions to the author.
Okay.
Yeah, I think it's a very, I think Ben pointed an interesting and important question, because back then in the 2016 Cummings paper in Science,
Yeah,
I think one of the reasons why they could reach it because they, I think the cementite, I think that is called. That's a left.
cementite.
That's brought by the glacial process. So because they go those ones because they really want to say, okay, this is a unbiased sampling of the crust composition. So actually, that's a very important thing. So because in the end, they want to reconstruct the crust composition, then you need to say that what does this sedimentary sample really represent? So I think Ben brought a very good point. To me, that they need to. I think they tried. They have made some more useful argument in the paper.
If you just exclude those data, this scale data, I think there's no correlation. Is right. Maybe the correlation is not real if you exclude some. This data is, I think, 4, 5, 7 data. Okay, any comments or questions we discussed here?
Actually, they still figure 4A for those rivers that with large elevation, they do have large loads, because for those several ones, for the Ganges, that's the one in India, Amazon in Brazil, Indus, and Andes Mountains. I think those ones that are with a relatively high elevation and also large. And long.
Yeah, because they are the one of those big rivers in Earth. Yeah.
No, okay, so I think this relationship holds. Probably it still holds.
Yeah.
But I think they also get us this. I think the horizontal axis here for the maximum elevation, that's natural process, but the sediment load had the interference of the human efforts.
Yeah.
Because for sure, there's no way that in San Francisco, as they put it there somewhere.
Yeah, because
and the Yangtze River too. There's huge human impact for it. And the Rhine River, in Europe, and there must be some other ways that to dramatically change the numbers.
It also affects by plants, and because if humans just destroy the plants along the river, right, more sediments would get into the river, I think. And also, I think I have to put just a figure here, and I think this figure in the Hackworth 2017, and they just have some another idea. This is the present-day neodymium isotope ratios from whole rock samples plotted against the topographical relief. The y-axis is the neodymium isotope ratios. The x-axis is the relief, and here is the neodymium model ages. So we can see that the crust with the arcane neodymium model ages tend to have the lower average topography, and lower neodymium ratios. It means that the older rocks are significantly underrepresented in the sedimentary rock. So maybe the sedimentary rock just tend to get more records from the younger sediments. Maybe there exists the sampling bias. I think they could not totally exclude this problem. I think it's a fact. I think.
Actually, I have another relevant question to this. So for all the rocks are significantly underrepresented. So do you mean all the rocks from the older stratigraphy, or do you mean the sediments that sample the older part? Because for the first part, I think that's easy to understand, because of course older age it is, the fewer samples there are. But for the second point that I raised about, might not be really true, because for the stable cratons like Yukon, or like say other cratons, they are stable and they're old. Their rocks are old, always old, and you have the river flow them, and then you get them. So I don't know whether they have some detrital zircon, other people's detrital zircon studies to suggest that what's the proportions of this different like the source rocks, because always a combination of old and new. To me, the source rock are always a combination of old and new ones to form these sedimentary samples.
Yes. Part of except for that, I think also the relief. To how did they get the relief of the old rocks? Because usually the new crust just produced usually with the higher relief or high altitude, but for the stable cratons, they usually gets the lower relief or low altitude, and it's not easier to affected by the erosion. And maybe this is a fake, or it's just artifacts by sampling bias. I think there's a lot of problems, and if you're using the sedimentary rocks to reconstruct this problem. So do you have any questions? Yeah, do you have any comments or questions that we discussed here?
Okay, I think that's so much about today. Okay, I will see you all probably tomorrow, tomorrow Wednesday. I think tomorrow. Okay, see you, and yeah, in case anyone would like for the talk. Okay, see you.